Calculating the demand for single-phase ranges and dryers on a three-phase service involves a few key steps to ensure accurate sizing of the electrical service. These steps include determining the maximum connected load, applying demand factors, and understanding how to translate that into an equivalent three-phase load. Firstly, determine the maximum connected load. To do this, calculate the total wattage of all single-phase appliances that will be connected between any two phases. This is a crucial first step because it establishes the baseline for the maximum potential draw from these appliances. Secondly, multiply the maximum connected load by 2. This adjustment represents the total demand under the assumption that all appliances are operating simultaneously. It's a conservative approach that helps in ensuring the electrical system is robust enough to handle peak loads. Thirdly, apply the demand factor from Table 220.18 in the National Electrical Code. Demand factors are used because it's unlikely that all appliances will be running at their maximum wattage at the same time. This table provides factors based on the number of units and the type of appliance. For example, if you have 50 apartment units with dryers, the demand factor might be 0.5, meaning only 50% of the total connected load is expected to be in use simultaneously. In the fourth step, the result needs to be taken into account regarding the voltage. For single-phase loads in residential applications, the voltage is typically 240 volts. The demand factor accounts for the diversity of use, acknowledging that not every appliance will operate at its maximum capacity concurrently. Now, let's go through an example to illustrate these steps. Consider a 15-unit apartment building where each unit has a 5 kilowatt dryer. Firstly, calculate the maximum connected load. The total connected load for the dryers is 5 kilowatts per unit times 15 units, which equals 75 kilowatts. Secondly, adjust the maximum connected load. Multiply the 75 kilowatts by 2, resulting in 150 kilowatts. This represents the hypothetical scenario where all dryers are running at full capacity at the same time. Thirdly, apply the demand factor. According to Table 220.18, the demand factor for 15 dryers is 0.5. Therefore, the demand is 150 kilowatts times 0.5, which equals 75 kilowatts. This 75 kilowatt figure is the estimated demand for the dryers in the apartment building. Finally, calculate the equivalent three-phase load. To size the three-phase service equipment, convert the single-phase demand into an equivalent three-phase load. This conversion involves multiplying the demand by a factor of 0.866, which is derived from the square root of 3 divided by 2, used to account for the phase relationships in a balanced three-phase system. In our example, the equivalent three-phase load is 75 kilowatts times 0.866, which is approximately 65 kilowatts. This value is crucial for selecting the appropriate size of transformers, conductors, and protective devices in the three-phase service. The demand factor from Table 220.18 is a crucial element in these calculations. It allows for a more realistic assessment of the load, avoiding oversizing the electrical service. The demand factor takes into account that appliances are not used simultaneously. The equivalent three-phase load is used to size the three-phase service equipment properly. This ensures that the equipment can handle the expected load without being excessively large or inefficient. In practical applications, it's important to consult the latest version of the National Electrical Code and local electrical codes to ensure compliance. Electrical codes provide specific guidelines and requirements for electrical installations, and they are updated regularly to reflect changes in technology and safety standards. Furthermore, it's essential to involve qualified electrical professionals in the design and installation of electrical systems. Electrical work involves inherent risks, and professionals have the training and experience to perform these tasks safely and correctly. Professional electricians can ensure that the electrical system meets all applicable codes and standards, and that it is installed in a way that minimizes the risk of electrical hazards. When calculating the demand for single-phase ranges and dryers on a three-phase service, firstly, accurately determine the maximum connected load by summing the wattage of all relevant appliances. This involves identifying each appliance, such as dryers or ranges, and noting their respective power ratings in kilowatts or watts. Then, add these values together to obtain the total connected load. For instance, if you have 10 dryers, each rated at 5 kilowatts, the total connected load would be 50 kilowatts. This initial step sets the stage for subsequent calculations and is crucial for ensuring the electrical system can safely handle the potential load. Secondly, adjust the maximum connected load by applying a multiplier, typically a factor of 2. This adjustment accounts for the scenario where all appliances are operating simultaneously, representing a worst-case scenario. While it's unlikely that all appliances will be running at their maximum capacity at the same time, this step provides a safety margin and ensures the electrical system is adequately sized to handle peak demand. Multiplying the maximum connected load by 2 effectively doubles the load, providing a conservative estimate for the total demand. For example, if the maximum connected load is 50 kilowatts, multiplying by 2 yields an adjusted load of 100 kilowatts. This adjusted load is then used in subsequent calculations to determine the appropriate size of electrical components. Thirdly, apply demand factors from Table 220.18 in the National Electrical Code to account for the diversity of use. Demand factors recognize that not all appliances will be operating at their maximum capacity concurrently, reducing the overall load on the electrical system. Table 220.18 provides demand factors based on the number and type of appliances, reflecting the statistical likelihood of simultaneous operation. For example, if you have 10 dryers, Table 220.18 may specify a demand factor of 0.6, indicating that only 60% of the total connected load is expected to be in use simultaneously. Applying this demand factor to the adjusted load of 100 kilowatts yields a demand of 60 kilowatts, representing a more realistic estimate of the actual load on the electrical system. Demand factors are crucial for avoiding oversizing the electrical service and reducing unnecessary costs. Fourthly, consider the voltage when calculating the demand. For single-phase loads, the voltage is typically 240 volts in residential applications. Voltage is a critical parameter in electrical calculations, as it directly affects the current and power relationships. The demand calculated in kilowatts must be converted to amps to determine the appropriate size of conductors and circuit breakers. To convert kilowatts to amps, divide the power in kilowatts by the voltage and then multiply it by 1000. For example, if the demand is 60 kilowatts and the voltage is 240 volts, the current would be approximately 250 amps. This current value is then used to select the appropriate size of conductors and circuit breakers to ensure the electrical system operates safely and reliably. Considering the voltage is essential for accurate electrical calculations and ensuring compliance with electrical codes and standards. Now let's delve into an example involving a 15-unit apartment building where each unit has a 5 kilowatt dryer to illustrate these calculations. Firstly, determine the maximum connected load. With 15 units each having a 5 kilowatt dryer, the total connected load is 15 units times 5 kilowatts per unit, which equals 75 kilowatts. This represents the total potential load if all dryers were to operate simultaneously at their maximum capacity. This initial step is crucial for establishing a baseline for subsequent calculations and ensuring the electrical system can handle the anticipated load. Secondly, adjust the maximum connected load by applying a multiplier. In this case, we multiply the 75 kilowatts by 2, resulting in an adjusted load of 150 kilowatts. This adjustment accounts for the possibility of all dryers operating simultaneously, providing a conservative estimate for the total demand. While it's unlikely that all dryers will be running at their maximum capacity at the same time, this step ensures the electrical system is adequately sized to handle peak demand. The adjusted load of 150 kilowatts is then used in subsequent calculations to determine the appropriate size of electrical components. Thirdly, apply the demand factor from Table 220.18 in the National Electrical Code. According to Table 220.18, the demand factor for 15 dryers is 0.5. This demand factor recognizes that not all dryers will be operating at their maximum capacity concurrently, reducing the overall load on the electrical system. Applying this demand factor to the adjusted load of 150 kilowatts yields a demand of 75 kilowatts, representing a more realistic estimate of the actual load on the electrical system. The demand factor of 0.5 indicates that only 50% of the total connected load is expected to be in use simultaneously. Fourthly, calculate the equivalent three-phase load. To size the three-phase service equipment, convert the single-phase demand into an equivalent three-phase load. This conversion involves multiplying the demand by a factor of 0.866, which is derived from the square root of 3 divided by 2, used to account for the phase relationships in a balanced three-phase system. In our example, the equivalent three-phase load is 75 kilowatts times 0.866, which is approximately 65 kilowatts. This value is crucial for selecting the appropriate size of transformers, conductors, and protective devices in the three-phase service. The equivalent three-phase load represents the load that the three-phase service must be able to handle, ensuring the electrical system operates safely and reliably. The 65 kilowatt figure is then used to determine the appropriate size of electrical components in the three-phase service. In summary, firstly, determine the maximum connected load. This involves calculating the total wattage of all single-phase appliances connected to any two phases. This step provides the initial value for assessing the total potential electrical draw. Secondly, multiply the maximum connected load by 2. This adjustment represents the total demand assuming all appliances operate simultaneously, creating a buffer for peak usage scenarios. Thirdly, apply the appropriate demand factor from Table 220.18 in the National Electrical Code. These factors account for the diversity of use, acknowledging that not all appliances will operate at maximum capacity concurrently, providing a more realistic estimate of the electrical demand. Fourthly, multiply the result by the voltage to account for the voltage characteristics of the single-phase loads, which is typically 240 volts in residential applications. These calculations ensure accurate sizing of electrical components in compliance with safety standards. Here are a few additional points to consider. Firstly, always consult the latest edition of the National Electrical Code for the most up-to-date guidelines and requirements. Electrical codes are updated regularly to reflect changes in technology and safety standards, so it's essential to stay informed about the latest revisions. Secondly, involve qualified electrical professionals in the design and installation of electrical systems. Electrical work involves inherent risks, and professionals have the training and experience to perform these tasks safely and correctly. Thirdly, consider the impact of future load growth when designing electrical systems. It's often prudent to oversize the electrical service slightly to accommodate potential increases in electrical demand in the future. Fourthly, ensure that all electrical equipment is properly labeled and maintained. Proper labeling helps prevent confusion and ensures that electrical systems are operated safely. Regular maintenance helps identify and address potential problems before they lead to equipment failures or safety hazards. By following these guidelines and working with qualified electrical professionals, you can ensure that electrical systems are designed, installed, and maintained safely and reliably.